Hi. Full screen. Move the pictures of your screens up here. Okay, increase my volume. I already cleaned up my board. How are you guys doing? All right.
All right.
Devon, Denward, Sebastian, Everly, Ray, Jaslyn, Matthew, Adil, Yoli, Yasmin, Margarita. I'm practicing names. Julian, Said, um, Alana, sorry, Feng, Andres. Okay. Getting there. There is one chat. There is, yes, this is it. Group me. Okay, great. I really like that. I really like that. Make groups, study with each other, share ideas, and don't use the group for other activities like when you're taking the exam. Stay away from the group when you're taking an exam, unless group discussion is allowed. The bonus point that I have in the syllabus, 1 point to be added at the end of the semester for making yourself visible and audible and your participation. I'm going to probably increase it to like 2%. So if you do perfectly in the semester, you get 100. And if you have been present and you have been participating, like not necessarily asking questions for that sake of asking, but then in general, then I'll add 2 points to your total. That could make a difference. Okay. So that's the carrot for being present and keeping your cameras on. All right. Um, any specific questions or any concerns? Dr. Mike, I don't like you. I'll take pictures of the board. Okay, are we recording? Yeah, this one and Chem8 is auto recording. I need to change that for my middle class, which is the, not middle class, the class in the middle of the day, 128 day. Okay. All right. Make sure that you guys create some groups. That would be great. Okay. Let's go to the board. Let's go to the board. The beautiful board. Okay. That's the board. I am going to close the window because otherwise it's gonna. It was supposed to rain today. Not enough cloud for rain. Okay. So I'll use the colors even though they are not very visible, like the green and the purple and the blue cannot be distinguished. But I'll use them and just for an experiment because I'll take still pictures of the board as well in the middle whenever I fill up the board. And if you guys still cannot see the colors in the still picture, which is supposed to be for better resolution, let me know. Then I'll stop. I'll drop these pens. We can figure things out as we go along. Okay. So this is Chem 128B, Tuesday, Thursday, and today is 2221. Okay. We are talking about spectroscopy. Okay. We talked about all kinds of random stuff on last Thursday, but today let's get serious. Spectroscopy. Spectroscopy. Okay. Anybody knows what you know what? I don't want to block this region. Let's write the spectroscopy here. I think it's still showing here. Yeah. And I think we need another color. It's not very visible. Spectroscopy. Okay. What is spectroscopy? Anybody knows what spectroscopy is? Don't write in the Zoom, in the chat, or don't make any gestures. Just unmute and talk.
I think you said last week was something to do with the vibration of molecules and the signals that they make. And
that's one kind of spectroscopy. But spectroscopy is when we have a molecule. Let me see if I have a molecule here. Let's say this is a model of a molecule. In the center you have a carbon. Let's say we have another CH3 here. I don't know what they are. Let's say this is chlorine, fluorine, and bromine. So this is some kind of a hydrocarbon with bunch of things. So when we have this molecule, when we are dealing with this molecule, and we are pretty confident, if you're working in my research group, or when I was a student and I'm doing the synthesis, let's say we made the compound, I know 100% with 100% certainty that we got the compound, but how do you prove that it's the right compound, right? So spectroscopy is the use of electromagnetic radiation in some way or the other to get the molecule absorb or emit electromagnetic radiation, and then measuring the incoming and the outgoing and seeing the difference and making sense out of it. Okay, if that makes any sense. So basically, seeing a molecule using different types of rays, like visible light is also some kind of ray or electromagnetic radiation. So I want to talk about that very briefly. I'm not going to throw numbers because I can't remember all the numbers associated. For that, we have, I think my eyes are itching. For that, we have the PowerPoint and the book. Okay. So I'm just going to talk about different types of electromagnetic radiation and which electromagnetic radiation range is used for different purposes, different spectroscopy and different other than spectroscopy, other purposes, and some magnetic radiations, electromagnetic radiations that we cannot use. Okay, let's start. Okay, I'm gonna go with my gut feeling and try to space them out. Okay, first we're gonna start with you know what? I don't think I need to underline them. So usually when we are dealing with a spectrum or electromagnetic radiation, usually when we are looking at an UV visible spectrum, let's say this is, I'm not going to tell you what magazine this is. I'm going to show you the back side. Let's say this is a spectrum, okay? An NMR spectrum or an IR spectrum or an UV visible spectrum. Usually the energy is less on the right and energy goes up as we go to the left. So generally the convention is that this is less energy. As you go to the left, energy increases. So the energy of the different electromagnetic radiation increases as I list different things up there in a very qualitative way. Right is less and left is more. Okay, you can see what this is. That's my secret. Okay, radio wave is the electromagnetic radiation that human beings have figured out to utilize for something, okay, and some things actually, that has the lowest power, okay? That, and then the next guy up is, I'm going to just shorten it because I really don't think we have so much space. Radio wave. No underlining, Mr. Maitra. Okay, radio wave. Then we have microwave. Okay, you might think that microwave is very powerful. It is not. Microwave is pretty weak. It's just a range of electromagnetic radiation that's a little more powerful than radio wave. You know what? Let me just put some. radio wave, microwave, then what? Infrared, IR. Okay. IR. Then we have the visible range. I'm going to write the visible range this way. I don't have any. No, there is no yellow. If this is yellow, pretend this is yellow. Okay, this is the visible range. So visible, all the colors are purple, then indigo, VIB, blue, violet, indigo, blue. I can't distinguish between these. So this is violet, indigo, blue, green, yellow, and orange. Good luck to us. Yellow and orange. This is it. And red. Okay. So red, orange, yellow, green, blue, indigo, and violet. Okay. I'm going to ask you a very quick, rapid question, and I want a rapid answer. Unmute yourself if you want to answer. No points attached. Okay. I'll try to block the screen. I don't think I can block the screen. Which visible light is the weakest?
Blue.
Red? Red.
For some reason, as I grew up, I had a completely wrong notion. I always thought that the red is the most energy rich light that we have in the visible range. Okay, and somehow these different light waves are actually, when we see, that's the way human eyes and human system with the brain are constructed, that we can recognize the cones and the what is the other one? Cones and the
Rods?
cones and the rod. It's also chemistry. A small molecule, retinoic acid, interacts or binds with a big protein, retinoic acid receptor in the eye. When the light falls, there are different types of conformations, different types of shape changes. And that shape change is perceived in the brain as different colors, okay? And some animals I have heard, I'm not a big expert on that, but because, and they apparently don't necessarily see exactly how we see things. Sometimes I've heard that birds see things more in UV or something like that. I'm not 100% sure, okay? Radio, microwave, infrared, because it's infrared on the other side of the red. And then we have what here? I picked up my violet pen. This is purple, closest to violet. What's that? What's here?
Ultraviolet?
Ultraviolet?
Ultra violet or UV. And then we have, well,
Gamma?
sorry?
Is it going to be the gamma?
Gamma, between gamma and alpha, UV, there is something else. Who knows? When you break your board, Well, I'm not wishing that. But when I break my bone, I chip my bone here.
An X-ray?
I forgot about those.
That's okay. And finally, gamma. I can't, we all have our disabilities. I can't draw gamma. My gammas look like mu. It's a problem. Gamma ray. Let me try. I think that's gamma. That's the closest gamma you're going to get out of me, okay? Don't complain. Okay. So if I have to like show them using some kind of cartoon representation of a electromagnetic wave, what is a wave? Well, you're standing by the shore of a small lake, right? You can see the other side of the lake. And some kids were playing there earlier, let's say Chevrolet Lake, and it's absolutely still. The water is still, there's no wind, there's no disturbance, there's no fish, nothing is moving around. There's a little boat, like a paper boat, like floating on the other end of the lake. And all you do is, well, I like throwing things, okay? I started growing up throwing things around. And so I was not the popular kid in the neighborhood. So if I take a rock and I just drop it here on the other side of the lake, let's say the span of the water is here, as I drop it, it creates a wave in the water. The waves moves around like a little snake moving upside down like a sinusoidal wave, and it eventually goes and transmits the energy that you have created over here by dropping the rock in the water, and that energy eventually propagates to the other end of the lake, Chevrolet Lake, and it starts to move the little paper-made boat, right? Or a little something, some contraption of a boat, right? So the energy transferred from this end of the lake to the other end of the lake, but did the water move from this side to the other side? No, it didn't, right? So that's energy. So you have energy passing through air and vacuum, and that's electromagnetic radiation. So I'm going to use my very crude way of describing which wave looks like what, okay? How do we describe it in a pictorial way with a picture, okay? So radio waves are long and boring. You can't even see the whole thing, okay? These waves are also pretty long. Infrared, shorter than that, okay? Red, maybe a little bit shorter. Violet, maybe, I don't know. Okay, ultraviolet, X-ray, that's no different than other things. Gamma ray, okay? So longer the wavelength, you can't even see the whole wave. I can't draw the whole wave of radio wave in under that space. Microwave is something like that, okay? This is a very pictorial representation, so don't take it too close to your heart. Take it with a pinch of salt, okay? This is just to give you a pictorial idea. So the red is like that. So let me ask you a question. Which of the 1, 2, 3, 4, 5, 6, 7, which of the 6 waves, you know what, let me erase this. This is nothing but distraction. Which of these 7 waves has the longest wavelength? Unmute and answer. Which one has the longest wavelength?
Radio waves?
Radio.
Which one has the highest frequency? Number of waves second per centimeter.
Highest frequency
Gamma.
is gamma.
Gamma.
Which one?
Gamma rays have the highest frequency.
Gamma. So maximum energy, highest frequency, and lowest energy, lowest frequency, but longest wavelength. So I'm going to write this down so that you guys don't forget, because you might see it in the first quiz, okay? I'm just going to write down something about it, okay? Longest, what color shall I use? Let's use purple for the wave. longest wavelength, shortest wavelength. Okay, what's the wavelength? Well, where should we do it? Well, let's do it right here. Okay. This is the wave. Let's say this is a wave. This is the main line, and this is the wave. How about green color? You may not see it very clearly, but don't worry about it too much. If this is the wave, then this distance this is your wavelength, or that's your wavelength. It's generally written in as lambda. Okay, I can write lambda without any grammar. Okay, that's lambda. Okay, or here to here, or down to down. That this distance, or this distance, or this distance. They're all gammas. Okay, wavelength. That's one cycle. Frequency, on the other hand, okay, nu equal to, I'm just going to write it down. Number of, let's cut this off. Number of waves per, either per length or per time. Per time. Per either 2 units. Either time or distance. The one that we were talking about last Thursday when we were looking at this presentation, and the one that was used in infrared spectroscopy, that was called, who remembers? That was wave number of waves per this is inches, this
Centimeter?
is
Centimeter.
per centimeter. There you go. Number of waves per centimeter. So one of the common units of lambda is often used common nanometer. Nanometer is something that you will be coming across quite often. 315 nanometer, 270 nanometer, something like that. 254 nanometer. Okay. When we talk about ultraviolet spectroscopy, the spectroscopy that we often talk about is UV visible. That we are not going to be talking about right now. We're going to talk about it later on. Okay, that UV visible spectroscopy is measured in lambda. Okay, lambda will be plotted against x-axis. Okay, less energy on the right and more energy on the left. So the lambda will be bigger on the right side and lesser on the left side. And it's going to be measured in nanometers, sometimes in angstrom. Okay, generally nanometer. The energy of frequency when it's time, it's one example is this is just an example. So I'm going to put like a star here. Star means it's one of the units. So one of the units of frequency with time is use the same color. Number of waves per second, and there is a name for it. It's a very similar name. I think the spelling is different. It's also a very similar name for an auto rental place.
Hertz.
Hertz. Okay, this is Hertz. Hz. Okay. With distance, number of waves per distance, that's what we talked about last time. Number of waves per centimeter. That's called wave number, and it's often called, written as mu with a bar. Wave number. I'm just going to be lazy. Number. Okay. So these are some of the common common units that you can think about. Okay. So we have radio wave, the weakest, little more powerful, more powerful, which we see with, more powerful, kind of dangerous. You don't want UV light to fall on your skin. Well, UV light also helps you synthesize vitamin D, I believe, vitamin D, but you need UV light, but you can't take a UV lamp and shine on your skin. I mean, one of our doctor friends actually was saying that there's a unit that you can buy when you are not getting enough exposure to the sun and you are vitamin D deficient. Most of us from our part of the world, in India, we are vitamin D deficient. I have no idea. It probably has something to do with the pigments in your skin or whatever. So he was talking about you buying, I mocked him. I made fun of him for doing that. He said that there is a unit he purchased from Amazon that's a UV light resource. You just turn it on and sit next to it and expose your back and chest and hands and legs to it. And I thought it was very dangerous. He said, no, it's all worked out. So UV light is necessary for doing chemistry in your body. Sometimes, you know, the cis bond and trans bond, right? When you have a double bond, the two big groups on the same side, up or down, that's a cis bond. When the groups are on the opposite side, it's a trans bond. You have learned it in alkenes when you studied in 128A. Light can actually sometimes flip the molecule from cis to trans, and it's pretty cool. It's pretty cool because light therapy is used to deal with for curing a disease. What disease are we talking about? You guys know it. You put the babies in light, sunlight, or artificial light to fix their problem inside the body. Which disease are we talking about? Do you guys know about it? You have to know. Somebody knows. The babies become turn a little yellow because of a molecule that gets accumulated in the body and it doesn't get out of the system. Then you
jaundice?
Jaundice. Do you know in jaundice what happens? The pigment, why do you turn yellow? I mean, I can get jaundice too. When I get jaundice, I become kind of like saturated, not saturated. I have high concentration of a compound called bilirubin or biliverdin that's produced from a protein, part of a protein called porphyrin. You know, the hemoglobin has that unit. 5-member compound with a nitrogen. It's called pyrrole. 4 pyrroles attached. It's a long story, but I'm just trying to go through it very fast. So anyway, there is this organic molecule, part of a protein, and that's called porphyrin. Porphyrin breaks down from a cyclic shape to an acyclic shape. Okay, and there is one 5-member ring aromatic compound, another 5-member ring. There is a double bond in between the second and the third 5-member aromatic ring, and then there is a bond between third and the fourth. So when they're cyclic, it can be porphyrin. When you cut the cycle and you open it up, so you have pyrrole connected to pyrrole 2, connected to pyrrole 3, connected to pyrrole 4. Can you imagine the molecule? So imagine 4 cyclic 5-member ring molecules, each with a nitrogen, okay? Pyrrole 1, pyrrole 2, pyrrole 3, pyrrole 4. Between the second and the third pyrrole, there is a double bond. This is extremely cool. When the double bond is cis, okay? The double bond is cis. Imagine my chest is the double bond. There is one pyrrole here, there is another pyrrole here, third pyrrole and fourth pyrrole. So 1, 2, 3, 4, double bond. And this is cis. So when the double bond is cis, my arms are kind of like this. Okay, I need to drop the pens. So when it's cis, at the end of the first and the fourth pyrrole, there is a carboxylic acid. So C double bond O, OH. C double bond O, OH. That's a carboxylic acid. There is one carboxylic acid here, and there is a carboxylic acid here. Imagine that. Okay. Cis. So all the pyrroles are kind of pushed toward the same direction. So my hands are like this. This is my shape of that porphyrin, the bilirubin molecule. What happens is you have heard about hydrogen bonding, and you have hydrogen bonding between hydrogen and one of the three elements. What are the three elements that must be present to form a hydrogen bond with a hydrogen? If this is an OH, there's a hydrogen sticking out here. So what can form a hydrogen bond with this OH, hydrogen? Only three elements can do that. What are they? What are they? Three elements.
Oxygen.
Yes.
And nitrogen.
Yes.
Fluorine.
Fluorine. Why? What periodic table property, what elemental property that they have that's highest for them?
Electronegativity.
Electronegativity. Awesome. So cis double bond, pyrrole 1, 5-member ring with a nitrogen, connected to a 5-member ring with a nitrogen, third and fourth, and you have the carboxylic acids, right? What happens when the carboxylic acids are like, basically you're putting food in the mouth of your puppy, okay? You're putting like dog food, right? So they're right on their faces. So this is a CO, C double bond O, OH, and this is a carbonyl from the other end, and this is a OH. So what happens is this OH hydrogen bonds with this carbonyl oxygen, and this carbonyl oxygen from the other side, hydrogen bonds with the hydrogen from this OH. So they're kind of locked. Two hydrogen bonds, and this is called, what kind of hydrogen bonding is this? Is this intra or inter?
Inter.
In INTRA or INTER? Which one?
ER.
No, inter is between multiple molecules. This is intermolecular hydrogen bonding, if there is any hydrogen bonding. If I'm shaking hands with you, that's inter, interracial, intergational, intergalactic, between galaxies, between nations, between people. Have you seen the dogs chasing their tails? So if you have a bunch of dogs in a room and each dog has a little treat tied to their tail, if a dog is chasing somebody else's tail, that's inter. If the dog is chasing its own tail, that's intra, TRA. Intra means within itself, within me. I am hydrogen bonding with my other part of my body. My right hand and my left hand are shaking hands. So this is intra, TRA. Keep that in your system. This is interhuman handshaking. This is intrahuman handshaking. So when you do a cyclization reaction, we have to do something funny with the concentration. We can talk about that some other time. Okay. So this guy, this molecule, the babies have, we have, ours is under control. Babies are not, because they haven't seen much light. So this is like this, right? So is the OH group a polar group or a non-polar group? What do you guys think?
Polar.
This is a fascinating discussion. I cannot resist talking about it. Okay, so this is a cis bond. Both the big groups are on the same side. Okay. These are the pyrroles. I'm just using some kind of cartoon representation, and you have carbonyl and OH. Oh, my scale is all screwed up. Carbonyl and OH. And there is hydrogen bonding here. and here. Okay, this is H bond. This is H bond. Okay, so let's draw a few more molecules. So I'm going to take breaks back in our past life, 128A life, just to give you glimpses and what I expect you to know and how you should recapitulate those materials if you have forgotten or if you have gone into the atmosphere. Okay, you need to really catch up. So this is important. Okay, so if we have a carboxylic acid, this is a carboxylic acid functional group. Okay, the smallest guy is hydrogen. That's called formic acid. The next bigger guy is acetic acid. Whenever you have a hydrogen attached to a pretty electronegative element such as this guy makes things very polar. Okay, because of the electronegativity difference, the electrons are pulled to this direction, electrons are pulled to this direction. So there is a delta minus charge, there is a delta plus charge. And you know, carboxylic acids are prone to losing their proton. Okay, it's like losing change. The proton is extremely loosely bound. You produce the O minus after you lose it, and then it resonates. We talked about it. Then I think we might do a very quick recapitulation or review of resonance and stuff like that. The bottom line is, this is very polar. Okay, this is very polar. Okay, whenever you have hydrogen attached to nitrogen, hydrogen attached to an oxygen, even your alcohol. Okay, why do you think alcohol dissolves in water? Ethanol and water. Why do you think they love so much that you can't even tell the difference between which layer is water and which layer is ethanol? Because there are no two layers. They're homogeneous. Okay, because there is hydrogen bonding here, there is hydrogen bonding here, and there is hydrogen bonding everywhere with the neighboring water and alcohol molecules. That's why they love each other. This is also pretty darn polar. This is also not very polar. This is polar. It's pretty polar. Okay. So whenever you have situations like OH, NH, pH, all this stuff, SH, not so much, they make the molecule very polar. When they're polar, they're more water soluble. It's very important. Okay. In this case, okay, unfortunately, there is hydrogen bonding. There is hydrogen bonding, intramolecular hydrogen bonding between my two carboxylic acids. And so this OH is busy doing hydrogen bonding with my right carbonyl group, and this, my right OH is busy doing hydrogen bonding with my left carbonyl group. Okay, that means their potency is reduced. That means this guy is already busy doing intramolecular hydrogen bonding, doing the handshake. My hand is not free to shake with your right hand. I'm too busy shaking hands with myself because I'm trying to hold on to myself in a tree. I can't shake hands. Don't try to be polite. Expect me to be polite when I'm hanging from a branch of a tree, and I have, fear of height. I'm afraid of dropping and dying, right, or breaking my bones. So I can't do that. So when the carboxylic acids are connected, are hydrogen bonded with each other, do you think the carboxylic acids will behave like a polar group, or their polarity is kind of messed up at this point? Is this molecule polar or not? Yes or no? What do you guys think? I could ask questions like this in the first quiz just to see, just to test the water. So when the carboxylic acids, let me just show you here. Okay, when they're hydrogen bonded, do you think they can interact with other stuff in the neighborhood, in the medium, to make them look like polar, or their polarity has been temporarily kind of like subsided? They're not so polar. My question is this polar or non-polar? This dude, this situation, is it a polar molecule even though it has two carboxylic acids? Is that molecule polar or not? Yes or no? What do you guys think?
Non-polar?
Why? Can you explain?
Because I think you said that when it's intra-connected, it reduces the potency of the polarity.
Yeah, because the hydrogens are being already used. I mean, if you have, let me see if I can use an example. A dog, right, is capable of biting, right? Can I'm not an animal hater, so don't spread rumors about me. I'm not a terrible person. I'm an animal lover actually. So if you have a dog that goes through some, you know, psychological outbursts once in a while, and when you're taking it out for a walk, and you know that neighborhood has many dogs, and you're putting like a little thingy on his face so that it cannot bite. So it's kind of like that. It's capable of hydrogen bonding, but it's already being engaged in hydrogen bonding with itself, with other part of the molecule. So what is it going to hydrogen bond in the neighborhood? It is being temporarily kind of, you know, like nullified, like neutralized its effect. So it's not very polar. Okay, this is what happens in the jaundice patient. This molecule is in cis configuration on that, in the middle of the molecule, and the molecule is folded like this, and the two ends of the carboxylic acids are hydrogen bonded with each other, rendering their polarity to be very low. They're not polar, they're very non-polar. It's very greasy molecule. Okay, these are some of the knowledge or little bits and pieces of your take on organic molecules properties that you should have picked up in 128A, hopefully. Okay, so this molecule is supposed to be very polar. It's not very polar because this hydrogen carboxylic acids are too busy, you know, making bonds with each other. So it's not available for making the molecule feel polar. Does it? I'm going to pause for a second because I speak too fast and sometimes it can be too fast. So absorb the material that we have talked about. It may be not related to IR, but then it's related to our knowledge, overall knowledge of organic chemistry, and that's what I'm trying to get from here. Okay, so far so good. Is there any gap in understanding what we have been talking about so far? Hydrogen bonding, carboxylic acid, which bond can be polar, and how they can make hydrogen bonding. This is an example of water and alcohol making hydrogen bonding. This is intermolecular, between two molecules, intergalactic. Okay, this is intra because it's within the same molecule. It's part of the two ends. So this is not very polar. So when it's not very polar, the way our body excretes extra molecules is by making them polar. That happens in the liver. Okay, that's called catabolism. When you are dealing with a molecule that's very non-polar, and if it doesn't get chewed up in the body, you are in trouble because that compound can cause toxicity because it's very greasy. If I eat grease, that's not going to be chewed up in the body by any mechanism. I might die from it, seriously. The body has mechanism by which a protein comes and oxidizes foreign molecules or any molecule that's produced in the system and eventually it gets out. This molecule cannot get out of the child's body or whoever is suffering from jaundice, and this molecule color is yellow. And it gets accumulated in the body, and you have accordingly have response, fever, sickness, lower appetite, etc., etc., etc. And if it's not treated, it gets messed up. So what do? You take the baby and put the baby under light. Okay, so you're basically using this electromagnetic radiation. This is not just for visualizing something, but you're using the visible light and UV light, not necessarily UV light, it's just plain light. When you shine light on it, okay? When you shine light, okay? When you shine light, something happens to the compound and the jaundice is cured. What do you think happens? When you shine light on this molecule, what do you think happens? Think, force yourself to think.
Is it hydrogen bonds?
Hydrogen bond what? Articulate,
Yes.
explain. Speak up because I need to hear you and maybe I can watch you too. Yeah. Do you have any idea? Again, more?
Let's see. Like sort of
So
like the extra energy kind of breaks them, I guess, or like
how do you
they switch between cis and trans basically, and that's your body.
Oh man, you got it. Yep. Okay. Okay. Maybe you don't have to talk about what you just said last. Okay, just keep quiet, lay low. But what you said then word is they need to unstick, right? This is not good for me to be water soluble. How am I going to interact with my water? I need to unstick this by hand before I can shake hands with water, right? I need to interact with the water molecule independently. So I need to first undo my hands tied together. I need to drop from the tree, have a fire engine come and take me down, and I'm still holding onto my hands as if I'm paranoid and will fall off. Okay, I have fear of height. I might actually do that. So I unstick my hands, then I shake hands with the fire guy and say, thank you very much. And this guy can hydrogen bond with water, rendering its solubility in water only after it unsticks. How does it unstick? Then what, maybe you can just take a quick break. Don't say, I want to force everybody else to think about it. How can this unstick? What has to happen on the other end of this molecule? And what do you think light is doing here to that part of the molecule? It's written shown in a different color. Light is messing up here. Light is doing something to that black cis double bond. What do you guys think is happening when light falls on that molecule?
Is it just breaking?
Sorry?
Vincent? Is it just breaking the bond?
Not breaking the bond. Light doesn't have enough power to break the bond apart. No, that's wishful thinking, but that doesn't happen. That'll get one of us Nobel Prize if we could completely dissociate the bond into two halves. There is actually chemistry for doing that. It's pretty cool. No, that doesn't happen. But think about it this way. Somehow I need to lower my hand. Take it away. What do you think is happening across my chest, which is connecting the two halves of this molecule? It's cis right now. I'm dropping some hints.
It's changing the orientation from cis to trans.
There you go. When it's trans, Denward already said that. When it's trans, then one side is here and the other side is here with their carboxylic acids. There is no way this guy can shake hands with each other. if I am put with some kind of cast, one hand is down and one hand is up, there is absolutely no way I can shake hands with me. Then I will be interacting with other people. Okay, this is introvert, this is extrovert. So this introvert molecule becomes extrovert. Now it can interact with water, hydrogen bond, hydrogen bond, hydrogen bond, all the interaction. That means after the light treatment, the molecule becomes trans, releasing the carboxylic acids from each other's grip and making them available to interact with blood and water and urine and everything else. The way every polar molecule gets out of our system. Okay, it's the river. It's the river, and the river, the medium of excretion is basically aqueous. We don't have like methylene chloride or alcohol flowing in our system. It's everything is taken out from our system by making them more soluble in water. So this guy can easily get out from the system by being water soluble. So this is how it happens. And that job is done by visible light, which is very cool. Makes sense? This was a completely slightly unrelated discussion, but I think this is how I want you guys to be excited about organic chemistry and feel motivated. Okay. This is lots of heebie-jeebie and lots of random stuff. I'm going to take a snapshot anyway. I'm going to make it available for you guys, and then we'll see what happens. Okay, I'm going to block the camera because I think taking the picture straight face on is the best way to do it. Okay, got it. All right. So this is, it was obviously not directly related to spectroscopy, but then kind of use of light, and just talk about molecules and reminding you, this should be again a reminder of what you may have forgotten, what you may have never learned, and what you need to do in order to do well in this particular course. I'm going to erase the board. Okay. Everything about bilirubin, biliverdin, and jaundice. Okay, so how are we doing with time? It's 4:20. Okay, we have 24 more, 25 more minutes. Okay, longest wavelength, lowest, shortest wavelength, lowest frequency, highest frequency. If you really want numbers, you should, I recommend that you go back to the PowerPoint, one of the two, not PowerPoint, the PDF, and then get those numbers. I don't remember all the time. Okay, highest frequency, most powerful, highest energy packed. Okay, this is the highest energy packed. Highest energy, lowest energy. Okay. What good is radio wave? Give me an example where radio wave is used.
Communication.
What kind of communication? Radio communication?
A walkie-talkie, maybe?
Walkie-talkie, radio. Radio is radio wave. That's where the word radio comes from. Something else. When you're speeding down the freeway and you see the favorite lights in your rear view mirror, the spinning red and the blue in the middle of the night, and your heart starts pounding. Okay, I'm afraid of cops. They're nice people, but my past is not very. No, I never had any terrible thing, but I used to speed all the time. That slowed down. I can't afford it anymore. So radar guns. Radio waves, not all of them, some of them. Most of the old ones, they're radio waves. Radar detector, many of them use radio waves for catching the radar gun. Something else, when you go to a mall, when you go to the airport, when you go to a shopping center, there are some automated something, and they use radio wave to detect you. What am I talking about?
Metal detectors?
No,
Mm,
the something opens
Yeah.
up, you walk in. The motion sensors, they're radio waves. Also, there are also radio waves used in a technique called NMR, which we will talk about sometime in the near future. NMR is radio wave, and something that's done to your, let's say if I hit the curb after I fall from the bicycle or motorcycle, and I hit my head, then I sometimes X-ray is not good enough. I get something else done. 3-letter acronym. What is that?
MRI.
MRI. MRI and NMR are almost identical. Very simple. When we talk about it, you will really get a kick out of it. NMR stands for nuclear magnetic resonance. What does MRI stand for?
magnetic. Is it video or
Resonance, I stands for what?
imaging?
There you go. Perfect. They're almost the same thing. Okay. What is microwave used for? Microwave, put your food, casserole of food and warm, right? Heat. Heating. It's also used for running some reactions sometimes, like chemical reactions. Not necessarily by heating. This has been a debated subject. I don't want to start talking about it, but I can get very carried away and waste the rest of the time. I don't want to do that. So I'm just going to say chemical reaction. Okay. I'm bragging. If you say Dr. Maitra or Shantanu is bragging, I'm bragging. I not bragging. I'm just saying that when I first came here, I was given some startup fund, and using the startup fund, I bought a microwave for running reactions. Do you know how much it cost? About $40,000. Okay, it's a small microwave. It's a microwave oven with a little, sample insertion area, and then the cool thing about it is that you can control the temperature and the pressure inside the vessel where you are actually doing the reaction. A lot of people in Asian countries or developing countries, they use microwave like a regular microwave, like a household kitchen microwave for running reactions. And there has been numerous accidents because the microwave has sparks in the back, right? Because electrical circuit and stuff. Sometimes when you're using when you're running a reaction inside the microwave, it uses vapors or gases or solvents such as ether. Ether is very flammable. Pentane, very flammable. Hexane, pretty flammable. Ethanol can be flammable too. So when there is too much vapor of flammable gas and there's a little spark, recipe for disaster. People have died too because they used to use microwaves for running like kilogram scale reactions using a huge microwave, like industry scale microwave, not meant to be used for chemical reactions. That's compromising with safety and hazardous conditions. So anyway, so they can be used like that. Infrared spectroscopy. Finally, you guys are thinking like, oh my God, it takes him so long to get to the point. Okay, infrared spectroscopy is used to make a molecule dance. I'm just going to write that down. Okay, we'll discuss that in details. That's the next course of actions. Okay, I think today is pretty much short. Okay. Makes a molecule dance. We'll discuss it. We have already gone through it. Visible light is good for seeing us. That's why I ask you to turn your cameras on so that I can see you. It's also used for curing jaundice patients. All you do is you walk around in the sun like an idiot. If I have jaundice and looking at the sun, and you get better. That's the best therapy you could think about, right? And if you could listen to music and if you could cure your Alzheimer's disease, wouldn't that be awesome? So anyway, so that's that. UV visible spectroscopy is also another spectroscopy. I'm just going to write something down. Don't ask too many questions right now because I'm not ready. I'm ready, but then that's going to be a big, huge distraction. So this is for electronic transition. Basically, I don't know. I mean, most of us do not teach molecular orbital theory. We generally use the simple hybridization theory to discuss bonding and all that stuff. But when you learn molecular orbital theory, you have bonding molecular orbitals and non-bonding molecular orbitals. From these two orbitals, then the next two orbitals, sometimes they overlap. So eventually, the bottom line is energy-wise for one molecule, for example, hydrogen molecule, we have these layers, energy gaps, and nothing in between. There are 2 electrons here. There is nothing. There is 1 electron here, 2 electrons here. Then there are 2 electrons here, something like that. Okay. There are gaps. They're quantized. There are gaps. They're not. You cannot find electrons everywhere. You can only find electron here, or here, or here, or here. So the top molecular orbital, it's called highest occupied molecular orbital, or HOMO, HOMO. The next orbital may not have any electron, but it's there. Well, how do you know it's there? From UV visible spectroscopy, because you see that transition, you see that energy being absorbed that matches that gap. Highest occupied molecular orbital, and the empty orbital, it's called lowest unoccupied molecular orbital, LUMO, LUMO and HOMO. Sometimes when you pass UV visible light through a molecule, these dudes jump up and then they jump back down and emit energy. So this absorption matches the energy right here, this wavelength, whatever that is measured in nanometer. If you are really keen to know exactly what those numbers are, you can go back to that the presentation or read the book. Okay, off the top of my head, I don't remember everything. That's used for electronic transitions, and you get UV visible spectrum or UV visible spectroscopy. That's also used for detecting compounds in mass spectroscopy, not mass spectroscopy, like high pressure liquid chromatography, HPLC. Many other devices use a UV visible like a detector to detect something is passing or not, because every time if some compound is passing through that UV visible detector, then it sends you a signal. It absorbs the UV visible radiation and it gives you a peak. Okay, they have a certain, you know, like a format. I mean, they have a certain look. Okay, that's that. We will discuss it later on. X-ray is used to see the solid phase structure, crystalline structure of a molecule. It can literally tell you that this molecule has an atom here, has a nitrogen here, there is an oxygen here, there is a carbon, 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 2 hydrogens, 1 hydrogen and a methyl group. So it's called diffraction. But in order for X-ray diffraction to work on your solid compound, number one, in order for this to work, the compound cannot be a liquid or a gas. It must be a solid, and it cannot be an amorphous solid. It has to be a crystalline solid to have geometric sharp surfaces. And when X-ray falls on it, it diffracts off of those surfaces. And looking at the diffraction pattern, you can back calculate and figure out where is every atom. Nitrogen diffracts in a certain way, N bond diffracts in a certain way, chlorine diffracts in a certain way. In the older days, people would have to like manually figure things out. Now the software is so awesome. Sometimes it just pops it out like it does the automated, like the AI basically takes care of it. artificial intelligence. Basically, the software reads the data and tells you this is how your molecule looks like. Okay. So my wife was complaining the other day that, my God, Dr. Brooks sends his compounds and mounts it remotely in Canada in one of the centers, which have really fancy and expensive X-ray diffractometer, and he gets his structure in like few minutes or few seconds or maybe within a day. Where my wife Kalyani would have to literally work on that data to make sense out of it and manually figure out the structure of the molecule. But this is the progress of science. Gamma rays, well, we haven't been able to use gamma ray in a very useful way, other than the fact that if you shine gamma ray, you're probably going to get cancer because it's going to literally shoot things out of proportion and completely screw you up. It can also like damage your nucleus. Okay, it can knock off protons and neutrons. I don't know exactly how the nuclear chemistry works. It's been a long time since I had taken a course in nuclear chemistry. It's been a very, very long time. Don't ask me how many years have passed since then. Okay, so this is a kind of a very qualitative look of the entire spectrum. I want you to know which one comes after one. I don't want you to know exactly the energies. So let me just share the screen quickly. And number 2, I'm just going to quickly share the screen, and I'm going to just sit down for a second and show you where we are. Infrared spectroscopy. Okay, where is my cursor? There you go. Blah, 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 analytical technique, which helps determine structure, destroys, etc., etc. You can read that. You can read infrared spectroscopy measures the bond vibration, making the molecule dance. Let's not worry about mass spec. Let's not worry about NMR. Let's not worry about UV visible, but electron transitions. Okay. Mass spectroscopy is not very different than what we are talking about right now. X-rays, microwaves, etc., etc. We talked about it. C is lambda nu. Speed of light, that's a relationship. Energy delta E is h nu. It's the same thing as here. So you can actually put lambda nu, the value of nu here, C by lambda. So energy of this wave is directly proportional to nu frequency. More frequency, more powerful. And since you can replace, you can basically substitute for nu with C by lambda, energy is inversely proportional to lambda. Okay, more lambda, less energy, less lambda, more energy, more nu, more energy, less nu, less energy. Okay, this is what I was talking about. You can look at it, the exactly where the energies are. 10 power minus 9 centimeter. Okay, that's the wavelength. Very, very, very small wavelength. Whereas radio waves, 10,000 centimeter. My goodness, I didn't even realize it's that long. So each wave in radio is literally, holy macro. That's 10,000, right? 4 zeros. 10 power 4 means 10,000. 10,000 centimeter. It's a super duper long wave. And this is a different scale. Energy kilocalories per mole. I'm not going to spend time on that. Okay, I'm going to pass through it. I'm just trying to see what else is here. Vibratory mode. Okay. Yeah, so that's what I wanted you to see. Like, if you really want the numbers, if you really like numbers, if you get excited from numbers, then you can go back and take a look at those. Okay, so I'm going to go back to the screen, and we have, how much time do we have? 36. We have like 9 minutes left. Okay, so we are going to focus here. This is going to be our focus. Okay, this region. I'm not scratching it off. This is where we're going to spend some time, this class and next. So infrared radiation, when you pass infrared electromagnetic radiation through a molecule, let's say you have a container and you have some compound in it, and you're passing infrared IR beam through it, what happens to that? Okay, different amounts of infrared radiation, okay, measured in centimeter inverse, they get absorbed to excite the molecule. So what I'm going to do is I'm going to draw a molecule. I'm going to draw a bunch of different functional groups. This will be a good time to basically review functional groups and everything that those functional groups are involved in for the materials that you have covered in 128A. Okay, so I'm going to kind of block everything else here. This is block. Okay, this is block. This is block. Okay, we don't need that. So we're going to just discuss this business, infrared. Okay, and we will talk about what exactly they do. We have already seen it in the presentation. So let's draw a bunch of different body parts. You know, you saw that how a molecule is represented with like pieces of springs attached to itself. Okay, so different springs and different strength springs, like tight springs, hard springs, loose springs, you know, they represent different types of bonds. Let's start with the simple stuff. Okay, carbon, hydrogen. I'm just drawing part of the body parts of the molecule. Okay, only highlighting certain parts. So this is a very significant bond. Okay, and this guy is part of an alkane. This guy is part of an alkane. Who knows what's there here? We don't care. Okay, so we are going to focus on this bond. This is a specific bond. Carbon-carbon double bond is also a very specific bond. But remember, carbon-carbon, this particular bond is a carbon-carbon single bond. And this particular CH is also sitting on a single bonded carbon, sp3. Review hybridization. So this is sp3. This is sp3. That's important because the energy absorbed by this CH is different than the energy absorbed when you have a double bond. Okay, so that's one kind. This is going to be a different kind of a situation. What hybridization is here? What's the hybridization of the carbon? Who knows? Who remembers?
sp2.
sp?
2.
2. Very good. This is sp2. Okay. This bond will be acting like a tighter spring needs more energy. Then you can have this molecule. This is going to be even different. It's going to take more energy from the infrared range. This is sp. Okay, and this particular CC bond will be different than this CC bond and that CC bond. Each bond, when they're single bonded, double bonded, and triple bonded, when they're sp3, sp2, and sp, the strength of that spring to dance, expand and contract and bend, right? All kinds of funny dance moves can happen. They can expand at the same time. Okay, they can expand this way, symmetric stretch, asymmetric stretch, and then you can have all kinds of bending. Scissors, I forgot what this is called. What is this called? Who remembers? It's not that YMCA song that I'm trying to mimic. Michael, are you there? What is it called? Rock. Is it rocking? Whatever. And then you have the two hydrogens or two something, and then they can bend this way, or they can bend the same way. There is a name for it. The first presentation that I had showed you guys, it lists all those different things. So if
I see what you mean. I think maybe you meant wagging.
Wagging. Which one is wagging?
And I think that's the, yeah, that one, the
That
symmetrical.
one is wagging. Okay.
Yeah, I think so. There's symmetrical and then asymmetrical wagging. I think.
Okay, that's wagging. Okay, so for each of these dance moves, like just imagine like you have a robot. You should. Okay, I'm getting distracted, but this is good distraction. If you want to see something really cool, if you haven't seen it, go to Google and look for Boston Dynamics. Okay, they are making artificial intelligence robots, and they have a choreographed dance with a song of 4 robots. I can guarantee you that you will be absolutely blown away by that choreographed dance between 4 robots. Boston Dynamics. You can find that. You can find it on YouTube. It is awesome. When I'm down and I've been rejected by another grant for another grant, I just go and watch something like that. It just lifts my spirit. Okay? I'm not a robot, by the way. I'm a human. Okay. So each of these, so this spring, that spring, that spring, this guy, this guy, this guy, they're different. So when they're contracting and expanding, they use different ranges of infrared radiation, and you see that as a peak. So when this guy is expanding, when they're stretching and contracting, you see an icicle-like peak. So the infrared spectroscopy is like a line from the top of the rectangle, the spectrum, and it just goes down when it's absorbing, stop absorbing, lowering, and getting down. So it looks like icicles. So basically, it looks like icicles hanging off of the roof. Okay, the location of the icicle tells you what kind of bond, what kind of spring are we talking about, and whether it is stretching or whether it is bending. Don't ask me anything about bending. Okay, you can ask Michael. Go bother Michael when you have questions about bending frequencies. I'm really bad with that. It's a confession. Okay. That's that. So these are important. We'll talk about that. Then we have a very important group that we often see, an OH. Okay. And then I'm just going to put like 1 carbon here and whatever on the other side. Methanol, ethanol, it depends on your imagination. So this spring is very important. This spring is also very important. This bond, okay, different parts of the functional group. C single bond O has a distinct location where that energy is absorbed in infrared spectroscopy. Okay, when you have a carbonyl, and something else on the 2 sides, whatever, you have something here and you have something else here. We'll be discussing carbonyl chemistry at the very end of the semester. So this is a distinct spring, and there is no way you can miss it. It doesn't matter what you have here, whether it's a carboxylic acid, OH, whether it's an ester, OCH3, whether it's hydrogen and hydrogen, formaldehyde, it's used for restoring dead bodies. It has a pungent, typical smell. I don't know why I remember that. I think when I was a kid and I would go to the hospital for falling sick every other week, I could smell the formaldehyde in that hospital. Okay, formaldehyde is H and H. When you have methyl and methyl, that's a ketone. I don't do it, but you guys remember, I think many of you probably know the smell of acetone. That's a ketone. So ketone will have a distinct location. Aldehydes will have a distinct location. Acids, carboxylic acids, esters, amides in proteins or other molecules. So they're very distinct. So other peaks that can be important is you have a methyl group, then you have a nitrogen with hydrogens. So these guys are also very unique. They show up in distinct areas. The carbon nitrogen, well, I shouldn't probably say it because if you ask me, I won't be able to tell where the CN bond shows up. Another important peak will be carbon triple bonded with nitrogen. Okay, this is also very unique. Okay, I'm just kind of listing all the different possibilities. So this triple bond and this triple bond they are going to be very similar. They show up at a certain region. So the bottom line is when you see the NMR, IR spectrum, and if you have done a reaction, let's say you have made a carbonyl molecule into an alcohol by reducing it. Okay, we will learn that chemistry. And if you run an IR, and if you see the hydroxy group, you should be dancing. But let's say our student starts dancing. Michael comes back and says, Dr. Mitra, I think I got it. I see a carbonyl peak. I mean, I see a hydroxy peak. But then I look at it and I see a carbonyl peak. Then his face drops, jaw drops. He's like, oh, do I have to clean it up today or do I have to rerun the reaction? If you also see the peak from carbonyl, that means bad news. Not all of it got converted into the alcohol. Okay, so it's very good in detecting functional groups. IR is awesome for that. It can't tell you, I have 90% this and 10% that, or almost 60% conversion. I only have like 40% left. It's not that accurate. No quantitative analysis, but qualitative, from the qualitative point of view, it's awesome. I always had an attitude about IR and I've been punished in my life. When the NMR was down, my wife would sometimes scold me like, why don't you go and take an IR? And because shouldn't it tell you like whether you have the reaction successful or not? I'm like, I think so. So, okay, Michael, can you go and get an IR, something like that, okay? So let's stop here, okay? Have a good day and have a good tomorrow. And we will see you guys on whenever that is. I'm losing track of time. Thursday 3:30, okay? I'm going to take a snapshot of this. I'm going to make both the pictures and the video available. Give me feedback. If the video looks horrible, just give me some feedback, okay? And if you, whatever you have in your mind, let me know and we will go from there. Have a good rest of the day. Bye.
Thank you. You too. Bye.
Yeah, take care.